You are welcome to this lecture. We were talking about the plate fin type heat exchangers. Now, today in this lecture, we will try to solve some numerical problem where we will try to estimate the heat transfer or the heat transfer taking place. It is basically a simulation problem we will try to solve, where we will try to estimate what is the amount of heat getting transferred in the plate fin type heat exchanger. So, now let us look into the details of this plate fin type heat exchanger, where you will find that all the heat exchanger dimensions or the details will be given with some inlet parameters, and accordingly we will be trying to solve what is the exit temperature of the fluid streams, and also we will try to estimate what is the amount of heat getting transferred. So, if now look into the details of this heat exchanger configuration, this has been taken from the book by Shah and Shekulik, the fundamentals of heat exchangers, and is the fundamentals of heat exchanger design. Particularly, I am sorry, this is fundamentals of heat exchanger design. In this problem, what has been told is the overall dimension of the heat exchanger has been given. So, before doing that one, let us look into the other parameters that has been already been told. Say here, this is basically a heat recovery exchanger, where the gas and air will be exchanging heat. So, the exhaust gas is preheating the air. So, as we can understand that the exhaust gas is preheating the air, means the gas is getting cooled and the air is getting heated up. So, this is the hot stream. So, this stream is a hot stream, and this air is basically a cold stream. So, we have a two stream exchanger, and as you can understand from the configuration that this is basically nothing but a cross flow type heat exchanger. So, these fluid streams are there in a cross flow arrangement. Then what has been given as the gas flow rate, you can see that the gas flow rate is given, and it is a volumetric flow rate. It is not the kg in terms of kg per meter cube or kg per second, it is in meter cube per second, and also its entry temperature is given. It is entering at 900 degrees centigrade at a pressure of 160 kPa kilopascal. So, the air details are like this. Its flow rate is 1.358 meter cube per second. It is the volumetric flow rate entering at a temperature of 200 degrees centigrade at a 200 kilopascal. Its inlet pressure. So, what we need to look at is the now the geometry. This is an offset strip fin. This is the specification where you will find it. This has been taken from the Kaizen London compact heat exchanger book, and this is an offset strip fin with 1/8. It was the nomenclature given in Kaizen London, and 19.86. So, this 1/8 stands for basically we will look into that part, what it stands for. Whether it is the lance length or the fin height or the fins, and this is of course the fin spacing, number of fins per inch. So, when we have this knowledge about the offset strip fin or the fin, this offset strip fin will all the details will be, it is expected to be known. That means, we will be able to find out its fin height, fin spacing, then what is the free flow area, and etc. So, then we have another information given to this is that the similar fin, the same fin rather, are used both in I mean for the gas side as well as in the air side. Both air and gas side will have the same offset strip fin 1/8 19.86. So, these are the things those are known. Along with that the fin height, sorry, the heat exchanger height, then width and the length of the exchanger has already been told. So, now if we look at this geometry, you will find that this is the gas flow area. I mean this is how the gas is flowing on this side, the air is flowing on this side. So, what is the frontal area for the air? The air frontal area is this much, is the air frontal area. So, the air is coming from this end and this is what is the frontal area, that is 1 meter by 0.3 meter. Now, if we look at the gas side, what we will find, what is the frontal area? We know that this is the frontal area, I mean the gas is coming from this side. So, it faces this is what is that surface area on for the gas. And what is that dimension? We already know this dimension is 1 meter and this dimension is also 0.3 meter. So, here in this case we have both the frontal area similar to each other. So, we have this information, the overall dimension of the heat exchanger is given, the fin details are given, the volumetric flow rate and the inlet temperature and pressure of the heat exchanger is given, and it has been told that, or it has been the construction of the heat exchanger, that means it is a cross flow type heat exchanger, that is also given. So, now you can look what we have to estimate is the exit temperature. I mean we have been told that the gas is entering at say 900 degree centigrade at a pressure of say 160 kilopascal, and this air is entering at a temperature of say 200 degree centigrade, and its pressure has already been told as 200 kPa. So, now what we need to find out is the exit temperature of the air and what is the exit temperature of the gas. So, when we know the exit temperature of each gas, we would be able to find out the capacity or the rating or the of this heat exchanger, how much is the heat load of this particular exchanger. So, looking at this problem, now it is not difficult for you because of your I mean previous knowledge. We have already talked about it, that this is basically a rating problem, or this is nothing but a heat exchanger performance problem. So, rating or heat exchanger performance performance evaluation or simulation, whichever name we tell it or we call it as simulation. So, we have been told about the geometry of the exchanger, we have been told about the inlet conditions of the two fluid streams, and all the heat exchanger specifications are known. We know about the fin details, we know about the flow arrangement, we know the overall dimensions of the heat exchanger, we know this is the length is 1 meter, 0.3 meter, 0.3 meter. So, basically it boils down to a simulation problem. So, if we have a simulation problem, and now what would be our approach to solve this problem. So, before going into that approach, we would now like to have a look into the fin details. As I have told you that this offset strip fin 1/8 19.86, what does it mean and what are the informations we which we have for about this fin. So, if we now look into that part, let us have a look into that part. So, these are the fin specification. If you go back to the Case and London compact heat exchanger book, you will find that this is the geometry corresponding to this geometry. This is what is given. So, as I was telling you that 1 by 8 what is meant, it is basically meaning that it is the lance length, or this is where this is the flow, where this is the flow side, and there after certain distance or the lance length, these strip fins are offset. So, here you can see from the top view that this fin and between this fin there is another fin in between. So, it is getting offset, and this lance length or the fin length is we often call it fin length, or we often call it lance length. So, this is equals to 0.125 or 1/8 of an inch. So, in terms of the meter, this is 3.175 into 10 to the power minus 3 meter. So, we have the fin pitch, the other parameter, as you can understand that 1 by 8 and 19.86, that 19.86 corresponds to the number of fins per inch, and this corresponds to 782 number of fins in 1 meter. In a meter, it would be able to accommodate some 782 number of fins. So, from there you would be able to estimate how many number of fins are there if we make 1 meter long length of this fin. So, we are going to get some 782 number of fins. So, this is one fin between one, this is it is having some finite thickness. So, between this point to the beginning of this one, this is the repetitive block, and this fin, this is the fin spacing. So, now we have the fin pitch. So, that will give you the fin spacing, and this is the plate spacing. This is the plate spacing means this is the fin height. So, the fin height or the plate spacing, that gives you the B is equals to 0.098 inch, or in meter this is 2.45 or 49 millimeter. And fin length or the lance length, already as I have told that it is 0.125 inch or 3.175 millimeter. So, we have the as soon as we have talked about the this fin, we know about the say this is what is the fin height, this is fin spacing, and the fin thickness is also given. Fin metal thickness, that is also given, it is 0.1 to 0.102 millimeter, and that is what is the fin thickness, that is this between this is 0.1 to 102 millimeter. So, now with this information you know exactly what is the free flow area. So, that is how the free flow area the fin the heat transfer area to the volume between the plates is also known, and also we know the flow hydraulic diameter. So, this hydraulic diameter is basically we estimate in terms of the free flow area and the heat transfer surface area and the length of the fin. So, from there we would be able to estimate this hydraulic diameter. It is already been given for this type of fin, and it is this much 1.54 mm is the hydraulic diameter of this fin. Then we have the total heat transfer surface area divided by the volume between the plates. So, this beta, this is an important parameter. So, when we know the overall volume of the volume between the plates, we would be able to estimate the total heat transfer surface area. So, because that is also again it is something where which we need. And another information that has been given regarding this one is the fin area by the total area. This is again something which is very important for us. If you look into this parameter, we will come across this value when we talk about the overall fin efficiency of the heat exchanger. So, if you remember that we have talked about this, this is that there are the two plates connected, between them there is a fin, and we have this eta f, the fin efficiency of a single fin, but it is not a single fin, there are multiple fins associated with it. So, we will correlate it with eta 0, and eta 0 and eta f you will find they are correlated by the overall, this is the overall fin efficiency, and they are correlated with the individual fin efficiency by this fin area by total area A f by A. So, that we will come across. So, all these values will be necessary, particularly for estimating the heat transfer or the simulation of the heat exchangers are given in this one. This we have taken from the Case and London book. So, it is not only this is about the geometrical part, then we have the characteristics of this fin. We have talked about the geometrical parameters, then we need to now talk about what is called the heat transfer and fluid flow thermohydraulic data. So, we have again talked about it, or we have shown you earlier that this is expressed as a function of J and F. This J is basically the Stanton number and Prandtl number to the power 2/3. So, that is here it is given as Stanton number, Prandtl number to the power 2/3, and this all these dotted points, these points are the experimental values. So, and this is the best interpretation. So, we will have both the numerical values as well as this graphical values for this 1/8 and 19.86 specification of offset strip fin. Similar type of different type of fins and with different geometrical parameters you will find in the Case and London book. Those who are interested can look into this, consult this book. So, here we find that both the J and F, this is J is expressed in terms of the Stanton number and Prandtl number to the power 2/3, and this is how it varies with the Reynolds number. So, we have to first estimate the Reynolds number, then we have to get and value, the corresponding to that Reynolds number we will be calculating this Stanton number, Prandtl number to the power 2/3 or the J value, and this Stanton number contains that heat transfer coefficient, that requisite what we are looking for a particular site. And we also have this friction factor, which will be necessary if someone wants to calculate the pressure drop. You may remember in some of our earlier calculations, we were trying to estimate the pressure drop occurring in the fin through the fin passages, and there we have been told about that okay, this is the friction factor. If you remember in that example, we have been told about the Reynolds number, and corresponding to Reynolds number and the fin specification, we are supposed to find like that the corresponding value of the friction factor. So, this is how we estimate the friction factor and the J factor, or the from the J factor we estimate the heat transfer coefficient. And so, as soon as we specify the fin, that means the fin details are known, we have all the geometrical parameters necessary for the fin, and we also know what is the friction factor or what is the J factor. So, please mind that these values have been estimated experimentally, but there are also correlations available for the offset strip fin or the wavy fin or for the different plane rectangular fins or others, and one can also use those correlations while estimating the heat transfer and pressure drop J and F factors from those correlations, but I mean at any time the experimental data are found to be more reliable. Okay, so now we will go to the next where we will I mean this is the cross flow exchanger. This expression, if we remember that we have this expression for the epsilon NTU and the CR value or the capacity rate ratio. So, here we find that this particular correlation is meant for the cross flow heat exchanger, cross flow type heat exchanger. So, these are the things which we have already come across, or these are the information already available to us. So, based on this available information, now we have to frame our try to solve this simulation problem, and one by one we have to go into it. So, as you can understand that since we are trying to solve this simulation problem where we have a complete knowledge of the heat exchanger geometry. So, if we have the geometry known to us, what is the approach that we will take? It's we have to think about like whether this LMTD approach will be applicable or not. So, if we look into the temperature differences, can we, but we do not know exactly what is the temperature difference, because we are trying to find out the exit temperature. So, we do not have the knowledge about the temperature differentials at the entry and exit. So, we will not be able to apply the LMTD. We can assume some kind of exit temperatures, but that will always give you a kind of iterative solution. So, we will not go into that. So, rather we will try to look whether we can have an estimate about the NTU, number of transfer units. If we look at this expression for the NTU, what it talks about is the UA by C mean. Now, let us look whether it is possible to estimate these parameters. UA tells you basically the overall heat transfer coefficient, or 1 by UA is the overall heat transfer coefficient that will have both the hot side, then we have the wall resistance, then we have for the this is for the hot side, then you will have the for the cold side, and there will be say eta 0 A hot and then H hot, and then you have the similar terms for the cold side, and this RW is the resistance offered by the separating plate. So, if it is a separating plate, the fluid is trying to flow from, heat is trying to flow from here to here. This because of this finite thickness of this wall, this will also give rise to some kind of resistance to the flow of heat, and that we have to taken into account here. So, theoretically speaking, we have the since we know the fin specification, we would be able to ideally calculate this AH. We would be able to calculate the overall heat transfer coefficient, overall efficiency of the fin, and this HH, that is the hot side heat transfer coefficient. So, ideally we are supposed to evaluate this UA. of necessary for estimating the NTU. And the other part, that C mean, what is the minimum capacity fluid we would be ideally able to estimate or evaluate, and we will be basically able to calculate the NTU value. And this, once we know the NTU, we know from this relation what is the epsilon. So, once we know the epsilon, our relations epsilon, from the epsilon is related to the inlet and the exit temperature, and we can easily calculate the exit temperature. And when we know the exit temperature, it is not difficult to find out the heat duty from the MCP delta T for the hot and cold sides. So, our basic aim would be to now estimate the NTU. When we find that we have to calculate the NTU, we need to now find what is the UA, and when we try to find UA, we need to find what is eta 0, and not only that eta 0, we need to find out HH and also the heat transfer surface area. So, for that we need to go systematically one by one. First of all, to start with, we need to have an idea about how many number of layers of air and these gas streams are there in this particular heat exchanger. And once we know the number of layers available for the gas and the fluid side, then we have an idea about the heat transfer surface area available for the gas side as well as for the air side. So, we will try to first estimate, because we have the overall dimension of the heat exchanger known to us, overall heat transfer, the number of heat overall dimensions of the heat exchanger known to us, then we can estimate the total number of layers for the air side or for the gas side, because we also know what are the number of the overall dimension of the fin and the plate thickness. I think we have missed about the plate thickness. The plate thickness has been given, what is that separating plate thickness, that has been given as 0.5 millimeter. This is equals to 0.5 mm. So, we know this point, this is the thickness of the separating plate. We know about the fin height, what is the fin height, that has already been told. So, we would be able to find out how many such layers constitute, if we put one over the other. In between, of course, there would be the other layers, one layer of hot fluid stream, one layer of the gas stream, and like that the total number of layers will constitute that heat exchanger. So, that would be the total heat exchanger like that. Similarly, number of layers on this side and this side will constitute the total dimension. So, since the total dimension is given, since the individual fin details are given, we know the separating wall thickness. So, we would be able to find out what is the number, or what are the numbers of the fins associated with on the gas side and the fluid side, the air side. So, based on that information, we will be able to do the other calculations. So, we will look into that in a other class. Thank you.